So, we are nearing the end of this semester in terms both of time and in terms of material. We just have one more set of notes to cover for chapter 19. All right. Now, it may not seem like this to start with, but this chapter really ties together a number of things that we have talked about before. All right. For one thing, this chapter looks at redox reactions again. Okay. And it relates some information that you can get from redox reactions back to the things that we have talked about previously. All right. So let's talk about a couple of things I've already mentioned this morning or this afternoon. It's actually afternoon now. The first one is, what did we say delta G represents? Well, we have two things that delta G represents. The sign of delta G tells us whether a forward reaction is spontaneous or non-spontaneous under standard conditions. And the second thing we can get from that is the maximum amount of work that we can get out of a chemical reaction. And that's what we're interested in here. Okay? We have become very obsessed as human beings in our society of getting from one place to another. We have no choice in that, at least if we want to continue to live our lives the way we've become accustomed to. We have to be able to get around. All right, now we have chosen to use the automobile for this. And moreover, most of us use gasoline-powered automobiles. And my view is that needs to change. Okay, I've held this view pretty much for my entire life. And finally now, as I enter my 60th year of life, we're starting to see this. Okay, we're starting to see this transition. And what's interesting too is that the president at the moment is considering making some or imposing some restrictions on car production to encourage the more use of electric cars. Okay, and I think this is a very sensible approach. However, it's not without problems. And again, that's something I also want you to understand, and we'll talk about at least to some degree in this chapter. Okay, what is the most efficient way for us to maximize the amount of work out of a chemical reaction? It's an electric motor. All right, we talked about this before. A gasoline motor, the type of engine that runs most cars, is only about 25% efficient. In other words, only about 25% of the energy that's consumed by the engine actually goes into pushing the car forward. The rest of the energy has to be dissipated as heat. And that's why your car needs a functioning cooling system. It has to be able to do that. If it can't do that, it's not going to work. Because your engine produces tremendous amounts of heat. And what you can think about is you're just dissipating that energy. Okay, you're not getting anything useful out of it, except maybe warming your car on cold days. But even that doesn't take anywhere near as much heat as your engine is cranking out. All right. If you compare that to electric motors, and electric motor technology has been around for over 100 years. Electric motors are about 90% efficient in terms of their conversion of energy to work. So it's a far more efficient way of getting energy or getting work from energy. Okay, now, you could very reasonably say, well, that also depends on how the electricity that's being used is produced in the first place. And that's a very valid argument as far as I'm concerned. Okay? Most of the electricity that we consume is still produced by combustion reactions. Either the combustion of coal or the combustion of natural gas. And though that is only about 33% efficient, according to my turbo engineer friends. So again, that's another issue. If we're going to continue to generate electricity as we have, then making the transition to electric cars perhaps isn't as efficient as we would like to think. However, there are other ways of generating electricity which are considered to be renewable, although that's kind of a questionable term in my mind. Okay, New Jersey has begun a program that's very controversial of building windmills offshore to generate electricity from wind. Okay, and wind is considered to be a renewable source of energy, although again, ultimately the energy that's expended in the wind does come from the sun. Okay, and of course another energy source that people have started to use is solar panels. Okay, where you take light energy and you convert it directly into electrical energy. Those are much more efficient ways of generating energy. All right, and if we continue to develop those, and I honestly think that solar is probably going to be the most effective, because one of the things that has surfaced about windmills is that they do have environmental consequences, especially on bird life, as it's been shown. And there's a lot of controversy right now over all the whale deaths that have occurred over the last few months and what is actually causing that. There are a lot of people that would like to say, oh, it's because we put windmills up. And at least there's circumstantial evidence for that, because the whale deaths occurred after the windmills were built. But the question is still, is there a direct tie? And that's not going to be an easy question to answer. And I hope we can answer it, because it would be really nice to know, is it these windmills that are causing problems with the whale populations, or is it something else we're doing? Or is it something that we have absolutely no control over? And again, that we can't answer that question yet. There are a lot of people that think they have answers, but we don't have answers yet. All right. So, essentially what we're going to look at in this chapter, which I think is really timely and probably the most interesting part of this course, if truth be told, is the tie between chemistry and electricity. How can we get electricity from chemical reactions? And this is something that is so important to us because we rely on it so heavily. If you're using a laptop, your laptop battery relies on technology very similar to what we're about to talk about. If you're using a phone, which I wouldn't recommend for watching class because the screen's too small, again, the phone runs off of a battery. All right, your electric cars. I've really gotten interested in e-bikes lately, and electric bikes use the same technology. All right. So what I want to do to start with is I want to bring up a couple of physics things that we need to understand in order to talk about electricity. Okay? And the two things that I want to talk about are voltage. Okay? Because voltage gives us a lot of information. Can anybody tell me, how would you describe a voltage that you measure across an electric circuit? What does it actually tell you? You know, say for example, you have, and I'm looking around my messy office, say I have a AA battery, and I put a voltmeter across that AA battery, and it tells me that the voltage the battery produces is 1.52 volts. What does that mean? Sorry? Yeah, essentially what... Okay, yeah. Okay, so another way of saying exactly what you said is potential. what is the potential for this battery to do work? Okay, and the units that we use for voltage are joules per coulomb. All right, that's something we need to remember. All right, but that leads us to another problem. Okay, and that is, what is a coulomb? And the coulomb is a unit of current. Or actually, coulomb is really a unit of charge. But one of the ways we can measure it is using electrical current. And the unit we use is the ampere, which is coulombs of current per second. All right, so you definitely want to remember those two units as we get into this chapter. Now, one other thing I'm going to show you here is the coulomb is the physics unit of electrical charge. All right. I'm not sure I don't remember what the historical roots of the coulomb are. Okay, but it was determined back in the 1870s or 1880s, somewhere thereabouts, that you could measure electrical charge in terms of coulombs, and it was named after a famous physicist. But we can also tie the coulomb to a number of electrons. And here's the relationship. 1 mole of electrons passed through an electrical circuit is equal to 96,486 coulombs. This is also known as a Faraday. Right? Faraday is also used as a unit of charge. And if you look at how capacitors are measured, they are oftentimes or the capacity of a capacitor in terms of charge is often written in Faradays. Okay, microfarads, or even or millifarads, or picofarads, and for really small capacitors. And basically, it's this relationship. So here's what we want to think about. We can actually count electrons by knowing how much charge we pass through a circuit using this relationship. So basically, if you pass 96,486 coulombs of current through a circuit, that's the equivalent of 1 mole of electrons, or 6.022 times 10 to the 23rd electrons. All right, so keep those in the back of your mind. We definitely will come back to them. And probably the most important one is the volt. All right. Next thing we're going to do is we're going to go back and start talking about redox reactions. This is something that I'm presuming you have seen before in Chem 1. All right. The simple redox reactions were covered in Chapter 4 in Chem 1. And most of us, at least at Middlesex, also went over the very first section of this chapter where we learned how to balance redox equations, or more complex redox equations, in acidic and basic solutions. All right. For my coverage of this chapter, I'm not going to get into those complex reactions so much. I'm going to look at more simple reactions that are easier to follow. All right. So let's start with this. If I look at the reaction here, in other words, I'm mixing a solution of silver nitrate with solid copper metal. Who can remember what is the potential type of reaction that we're looking at if we have these two reactants? Think back to Chapter 4. You learned about combination reactions. You learned about decomposition reactions. single replacement reactions, double replacement reactions, combustion reactions, and acid-base reactions. Which of those... Go ahead. Yeah, okay, this is a potential single replacement. Now, how could I decide if a single replacement reaction is going to go given these two reactants? What would I look at? Again, I don't expect you to be able to predict this. I can predict it, but I don't expect you to be able to predict it. I just expect you to be able to know where to look to find the answer. Where would I look? Which table? No, not solubility. That's for double replacement reactions. What's the other one? What's the one that's, if you look at your lab manual, it's on the same page as the solubility rules. And basically, it's just a ranking of elements. It's known as the activity series. And what we learned from the activity series is that if you look at a reaction or a potential reaction such as this, and you identify the ion, which is silver in this case because it's tied up as silver nitrate, and the metal, if the metal is above the ion, then you know that this reaction will take place. Okay? Another way of thinking about this, and your textbook actually uses this language, is that this is a displacement reaction. Okay, what you could think about is, given the fact that we see the metal is above the ion, the copper is going to displace the silver ion from solution. And so in this particular case, what we would expect is this, and what we would observe, we see the formation of blue copper 2 ion. So that means we're forming copper 2 nitrate in solution. And we also see beautiful crystals of silver metal crashing out. All right, I need to reshoot this, but about over 10 years ago, I used a low resolution camera to shoot this reaction. And even with the low res camera, you could see the crystals of silver. I need to reshoot it at 1080p because you could really see them then. All right, it's really a nice reaction, and the solution turns blue. And again, that's indicative of the formation of copper 2 ion in this. Is this chemical equation balanced? No. Yeah, we're going to have to balance it, right? We have 2 nitrates on the right, so we're going to have to put a 2 in front of silver nitrate, and we're going to have to put a 2 in front of silver metal in order to balance this. Okay, now, that's the full molecular equation for this. What we're going to do primarily in this chapter is we're going to focus on net ionic equations, because net ionic equations help us to see where the action is. All right, so one of the approaches that I could take with this reaction that I've written, now that it's balanced, is I could say, okay, what's the spectator ion? Nitrate ion is the spectator ion. Okay, I've got 2 nitrate ions on the left, I've got 2 on the right. Those are spectator ions. All right, so what do I end up with then? If I want to write a balanced net ionic equation, I'm going to keep the 2 in front of the silver ion. My products are now going to be copper 2 and 2 atoms of silver. Or in the terms we've just been talking about in the previous chapter, I could say, all right, if I mix 2 moles of silver ion with 1 mole of copper metal, I'm going to get 1 mole of copper 2 ions in solution and 2 moles of silver metal. All right. So the next question I want to ask you, actually 2 things I want to point out. Number 1, the balanced net ionic equation is still balanced. Okay? And again, you want to make sure you be able to do that. You've got to be able to write balanced net ionic equations. And one of the things that you need to remember, one of the keys to success to writing balanced net ionic equations, is that the charges on both sides balance out. They don't have to add up to zero, but they do have to balance out. And we can see that here. If we add up the charges on the left, I have 2 times plus 1, and I have 1 times 0. So the sum of those charges is plus 2. On the right, I have 1 times plus 2, and I have 2 times 0. So again, those add up to plus 2. All right, so as long as I've got that balance as well, then I know I've done the right job. Okay, next thing. What's oxidized in this reaction? Is it the silver ion or is it the copper metal? Which one?
Copper?
Yes, the copper is oxidized. And so by default, what would we say about the silver? Yes. Okay, so let's write that down. And we want to be specific as well. The copper 2 ion, okay, it's the reactant, is oxidized. Except it's not copper 2. What am I saying? The copper metal is oxidized, not the copper 2 ion. Okay, there's no copper 2 in the reactants. And what we can also say is that the silver ion is reduced. All right. One of the easiest ways I've found to remember this is that reduction involves reduction in oxidation number. So for ions, it's just reduction in ionic charge. So the silver ion goes from plus 1 to 0. All right, now, the other thing we want to review, and we'll talk about this quite a bit in this chapter, is that you can split a reaction like this into 2 half reactions. In other words, I can write the oxidation half reaction, starting with copper metal. And we know that this is a 2-electron oxidation. Okay, so if I write a half reaction as an oxidation, then the electrons that are produced from that oxidation are a product. Okay, some textbooks, and I don't think Alex does this. I hope they don't, because I find it confusing. They write CuS minus 2 electrons gives us Cu2 plus. All right. We tend to shy away from those kinds of things, although not everybody does. And so you could rewrite the half reaction that way. There's actually nothing wrong with it. It's just that you have a negative sign in there, which you don't really want. All right. Similarly, what we can say is that the reduction half reaction is this. If we have silver ion in solution, to reduce it back to silver metal, I have to add 1 electron. Okay, now, if we're going to add these 2 half reactions together, as we have done in this particular case, then we also have to multiply the second half reaction by 2. Okay, and that's another hallmark of a balanced redox equation, is that in a balanced net redox equation, such as the one we have here, the number of electrons gained has to equal the number of electrons lost. All right, so why are half reactions so important? It's because we can take a redox reaction such as this one, and we can separate the half reactions from one another physically and actually generate an electrical potential. That's the principle behind any battery that you run across. Whether it be something as simple as a dry cell battery or something as complex as a lithium ion battery, they do exactly the same thing. Basically, what they're doing is separating the half reactions of two redox reactions. Okay, so that's what we want to think about. How do we compartmentalize something like this? And really, the technology has been around for millennia. Right? That's what I find amazing about this, is that I think and actually there's a lot of evidence that supports this, that there were societies that existed thousands of years ago who understood at least some of this technology. All right, one of the things I remember seeing, and it was quite a while ago, it was about 30 years ago when I first moved to New Jersey. There was an exhibit on at the Museum of Natural History in New York of some jewelry that had been found in what's now Peru, that had been dated back 3,000 years, or I think even as far as 5,000 years. And the thing that really captured me was, first of all, the beauty of this jewelry. But if you looked at it carefully, the people that made it understood electroplating, which is based on this technology. They knew how to electroplate silver and gold and copper. And they could do it with such intricacy and artisanship. It was just amazing to look at. And to me, it was really interesting to see and beautiful at the same time. If you ever get a chance to look at things like that. So my point is that even though by our standards we would say, 5,000 years ago, that was pretty primitive, these people understood electrochemistry. And they used it to their advantage. They used it to make beautiful things. All right, so just because we're very Western centric in our understanding of things, and it's based on what happened in Europe, but there are a lot of these other societies that perhaps didn't survive and didn't record information, but they understood quite a bit. And these people that lived in Peru, they're considered pre-Inca because they existed before the Inca tribes established themselves in Peru. It's just amazing what they could do. All right. So what we're going to do is we're going to talk about this. And again, it's fairly simple. They obviously did it by trial and error, but they figured out what they had to do to make electric currents and to electroplate metals, which is pretty amazing. All right. So let's look at another single replacement reaction. In this particular case, I'm mixing zinc metal with copper 2 ion. Is this reaction spontaneous or non-spontaneous? Or, if not being able to answer that necessarily, how could we assess if this reaction is spontaneous or non-spontaneous? You can think back to what we just talked about, or you can think back even further using some of the ideas that we just discussed in introduction to this chapter. How do I predict the spontaneity of this reaction? Okay, and again, I probably should qualify that question to say, all right, am I talking about qualitative terms or quantitative terms? This is another potential single replacement reaction. So how could I predict whether this reaction is spontaneous or not in qualitative terms? What did we just mention in the previous set of pages? we could do that. Okay. I'm actually thinking about something even further back, but I am going to do that. So I'm glad you brought it up. What else could we use? What else could we use to decide if this single replacement reaction will go or not? Exactly. We could use the activity series. If we use the activity series, we could say, all right, come on, here's the metal, and here's the ion. Is the metal above the ion in the activity series? And the answer is yes. Okay, now somebody said very wisely we could calculate delta G for this reaction. Let's do it. Okay, we've got the information to do it. Hopefully you still have it out from a few minutes ago. In the products of this reaction, what do we have? We have 1 mole of copper metal. All right, that's elemental copper, so the delta G of formation for that is going to be 0 kilojoules per mole. Again, if you don't remember that, you can just as easily look it up because you'll have that information available to you. But we also have 1 mole of zinc cation in solution. So we'll have to look up the standard Gibbs free energy of formation value for that. And it is in solution. I really should include the state symbols here. It's not zinc ion in the gas phase. Okay. In our products, we have 1 mole of copper 2 ion in solution. And we have 1 mole of zinc, of elemental zinc. And that has a standard Gibbs free energy of formation value of 0 kilojoules per mole. Again, you could look that up if you doubt me. Okay, so we need to look up 2 things. We need to find the standard Gibbs free energy of formation value for copper 2 ion in solution and the standard Gibbs free energy of formation value for zinc ion in solution. Okay, 65.49. That's kilojoules per mole. Okay. Negative 147.1 kilojoules. Yeah, it's a lot less. Okay, and actually you'll see that these are tied to the activity series. Okay, so we're going to take negative 147.1 kilojoules and we're going to subtract from that 65.4. If we do that, what do we get for our delta G? Okay. Yeah. So, in addition to our qualitative estimation based on the activity series, which, by the way, is tied directly to Gibbs free energy of formation values, and you might actually see that with these 2 ions. But more importantly, we know that this single replacement reaction will go. Some of you might even remember seeing it. Okay, it's one of the most common ones that's done. Okay, so this reaction is spontaneous at standard conditions, 25 degrees Celsius, according to this. All right, so if we were to start with a 1 molar solution of copper 2 and we threw in some zinc metal, we would end up with copper metal and zinc ion. And if the reaction was perfect, we'd end up with a 1 molar solution of zinc ion as well. Okay, that's another implication of standard conditions. All right. So it is spontaneous. So now what we're going to do is we're going to say, all right, let's separate this reaction into half reactions. All right, so let's do that. So we have two half reactions. I'm going to start with the oxidation half reaction, and then I'm going to go to the reduction half reaction. The oxidation half reaction involves stripping 2 electrons away from a zinc atom. And the reduction half reaction involves adding 2 electrons to copper 2 ion. Okay, nothing really difficult about that. So now, how do I separate these things physically? Let's think about that. Here's what I'm going to do. I'm going to take a beaker. And I'm going to take a second beaker. Into the beaker that's on the left, I am going to place a solution of zinc cation. Okay, now obviously there's got to be an anion in here as well. Okay, but I've got this solution of zinc cation in there. Okay, into that solution, I'm going to place an electrode that's made out of zinc metal. Okay, in the other beaker, I'm going to place a solution of copper 2 ion. And I'm going to place in that solution an electrode made of copper metal. Okay, my drawing isn't so great. Sorry about that. Actually, if you want to follow along, you can turn to the next page of the notes. It's all there. Okay. So what have I done? I've enabled one half reaction to take place on the left, the oxidation, and the reduction to take place on the right. That's a useful thing to remember because it follows a convention. Okay. So now, in theory, if I connect these 2 electrodes, I should see electrons moving from left to right. Okay, now here's the problem. There's one piece that's missing here, and this is a crucial piece to any battery technology. Because if I just set this up like this, and I actually did this live once for a class on Zoom. I set up a desk cam and I put this whole thing together and I connected it up to a voltmeter and we saw nothing, okay? There was no voltage for this cell as we've set it up. And here's why. Because if electrons are going to move through this wire from left to right, I'm going to build up negative charge over here on the right and positive charge on the left. I can't have that happen. I have to balance the charge somehow. Okay? The way I'm going to balance charge is I'm going to have to allow the movement of ions through some other mechanism back and forth between these 2 solutions. All right, there are a whole bunch of different ways that this can be done. And this is actually one of the biggest challenges of developing a usable battery in the first place, is that you have to be able to provide for this movement of ion between one compartment and the other. And you have to provide it as quickly as the electrons move, otherwise the battery won't generate any current. All right, so the most common way that this is done is, or at least for batteries of this type, is you just put some kind of solution in a tube and connect the 2 things together. So if we take a U-shaped tube And we fill that tube with a solution that allows the movement of ions. Okay, one of the most common ways to do this is you take a U-tube and you fill it with gelatin that's saturated with potassium chloride or something like that. All right, this way, what happens is if electrons move from left to right, then you're also going to see cations moving from left to right, and at the same time, anions moving from right to left. That way you balance the charge. Okay, this is known as a salt bridge. And again, it's essential. If you don't have a salt bridge, you're not going to have a working battery. All right. Now, one of the things that I learned when I was putting together the lab manuals years ago is that you can actually make a reasonably crude salt bridge by taking a piece of paper towel and soaking it in saturated sodium chloride solution. That actually works remarkably well. I was surprised at how well that worked. Okay, and actually there are some batteries that use paper or cardboard that is saturated with an ionic solution as a salt bridge. Okay, now that's actually been one of the biggest challenges to developing lithium-ion batteries is making a salt bridge that's robust but can also move large quantities of ions through it. Because if you think about it, even a battery that runs your cell phone, it has to be able to produce a couple of amps of current at peak load. And if the salt bridge isn't up to moving that many ions through it, then it's not going to work. Okay. So, here is a better diagram of what I'm talking about. All right. We refer to this type of cell as a galvanic cell because we're not really interested in the work that this can do so much as the potential to do work. In other words, we're interested in the voltage that this thing produces. Okay, if we were engineers and we wanted to redesign this cell to use it commercially, we would have to make a much more robust salt bridge. But again, this is kind of a standard thing. All right. And there are some conventions that we have to follow in order for this to work. Okay, that's what we're going to talk about next. The language and the conventions. And you would do well to take some time to learn this. Okay. So, the first thing I want to show you is that we can write out chemically what's going on in this cell very simply. And that's what's shown here up at the top. This is what we would call a cell description. Okay? You have two sides to the cell. The salt bridge is shown by this double line in the middle. Okay, that means those two sides of the cell are separated by a salt bridge. On the left, we have the oxidation half reaction. On the right, we have the reduction. And that's one of the first things that you want to remember. It makes this all easier. When you write a cell diagram such as this, or when you diagram it out like I did on the previous page, reduction on the right. Okay, now we have to apply terms to these that fit with the physics as well. Okay, and so we use the term cathode to describe the side of the cell where reduction takes place. And we use the word anode to describe the side of the cell where oxidation takes place. Again, the mnemonic that I learned many, many years ago, and it's stuck with me because the professor got, he was pretty pushy about it, is reduction and cathode both begin with consonants. Oxidation and anode both begin with vowels. Okay, that's one of the easiest ways to remember this, at least when you're starting out. Okay, so there it is. And again, in this convention, electrons are going to flow from left to right. Okay, now, another convention that we follow is we could actually calculate the potential for this cell by adding the potentials for the two half reactions together. Okay, now, that's a little bit of a stretch, but it does work. All right, it's not that a half cell itself is going to generate voltage. That's one of the most challenging things that we have to explain here. You're not going to have a reaction take place unless you have two components. You have to have an oxidation and a reduction component in order for a cell to work. There's no way around that. But we have data that enables us to calculate the potential for these cells, and we'll talk about that. Okay, we'll use it before we're done today, and then we'll pick up on that next time as well. We can use standard reduction potentials from a table. And that's something we will do. All right. I have a little bit different way of approaching that than most textbooks do. And I have my reasons for it. Okay. But nonetheless, I'll show you how to do that. But here's another thing we can say. We could calculate the standard potential for a cell such as the one we've just done by knowing the delta G0 for it. All right. Moreover, if we predict, as we have done, that a reaction is spontaneous, that means if I set up this cell and I run a wire from the anode to the cathode, I'm going to have a positive voltage. Okay, there's going to be potential to push electrons from the left side of this cell to the right side of this cell. Okay, that's another thing this tells me. Another thing I can think about it is if I can calculate the standard cell potential, that gives me another way of determining a delta G for a reaction. So there's your fourth equation for using or for getting a delta G0. You have the Gibbs-Helmholtz, you have using standard Gibbs free energy of formation values, you have the relationship between delta G and an equilibrium constant, and now you have the relationship between delta G and a standard cell potential for a redox reaction. Okay, so let's use this. N is the number of moles of electrons that are transferred if the reaction were to go to completion. Okay, F is this Faraday constant that we brought up before. It's basically 96,500 coulombs per mole of electrons. And I should really throw that in there because that's important. Okay. Remember too that if we're calculating a standard value, whether it's a standard Gibbs free energy of formation or standard Gibbs free energy, a standard potential, a standard enthalpy, or a standard change in entropy, that means we're talking about 1 molar concentrations. And if we have things in the gas phase, the pressure is constant at 1 atmosphere. All right. So let's go back and look at this reaction again. Maybe I did this already. No, I didn't. Okay. Here's the reaction we looked at before. What did we say the delta G0 for this reaction was? Flip back in your notes and look that up. What did we say it was? Okay. And what are the units on that? Yes. Negative 212.6 kilojoules. Okay. Now, we want to calculate the E0 for this. In other words, what's the standard potential of this cell? If I set up a cell where I have 1 molar zinc ion in my left compartment and I have 1 mole of copper 2 ion in my right compartment, or 1 molar solution of each, what's the potential that cell would generate? Okay, so I need one other thing. If I start with 1 mole of copper 2 and 1 mole of zinc, how many moles of electrons do I have to transfer to form 1 mole of copper metal and 1 mole of zinc ion? Is it 1? Let's go back and look at the half reactions. According to this, to oxidize 1 mole of zinc, I have to take away how many moles of electrons? 2. And same with the other. Okay, so what that means here is that this cell, one more, sorry, has an N value of 2 moles of electrons. Okay, now let's rearrange this equation. The E0, in other words, the standard potential for the cell, is going to be equal to negative delta G0 divided by N times F. Okay, now, what did we say the units for voltage were before? They're joules per coulomb. And so what that means is we need to transfer our value, our delta G value, into joules. So we're going to multiply by 1,000. So we get 2.126 times 10 to the 5th joules. Okay, so now we can plug that in. So the E0 for this cell would be negative 2.126 times 10 to the 5th joules divided by 2 moles of electrons times 96,500 coulombs per mole of electrons. Okay, and so what that means is if we do this all correctly, we should get the units joules per coulomb, which is the same as a volt. What do we get? Okay. .12. All right, so what that predicts, again, and we could check this out. I actually have this. I should dig up this video footage because I shot it and where I did this. And you actually take a 1 molar solution of copper 2 ion, a 1 molar solution of zinc ion, put a piece of copper metal in the copper solution, put a piece of zinc metal in the zinc solution, connect them with a wire, and then connect the two solutions with a saturated paper towel, and you get actually about 1.10 volts as your potential. So it does work. All right, so what's the point of this? The point is, again, we have this other quantity that we can relate to delta G. But the other thing you could think about is, given this relationship, if you know the standard potential for a redox reaction, then you could predict its spontaneity from that. Because if the standard potential for a redox reaction is positive, that means delta G is negative. The reaction's spontaneous. Okay. Oh, there it is. So we already did that. So we said, okay, the E0 we predict is 1.12 volts based on our values. All right, now let's do something different. Again, we have all these tables available to us, and I do not expect you to remember anything from these tables. I expect you to know how to use them, which does take practice in and of itself. You can't just go in there and look at these things and know what you have to do. Okay, so I'm going to take a different approach to this. I'm going to say, okay, now I'm just looking at this cell. I need to be able to do a bunch of different things with this information that will give me the ability to determine the standard potential for this cell. Okay, so here's what we're going to do. We're going to start out by looking at the cell diagram, and we're going to divide it into two components. There's the anode, and there's the cathode. And again, that double line is the divider between the two. Now, I'm not sure how Alex does this, but sometimes because of the limitations of HTML and everything like that, you can't diagram it out this way, and instead forward slashes are used. So what you might see in Alex is this instead. Zinc / zinc ion, and really I should put the state symbol in there. Double / copper 2 ion / copper metal. Okay, the top way is the typewriter way. If you have the ability to do equations, then you can do the vertical slashes, which is what I learned to do when I was an undergraduate. Okay, but when we typed papers back in the bad old days when we used mechanical typewriters, and I am old enough to remember that, we used slashes like that. Okay, so you might see that in Alex. I can't remember how they did it. But nonetheless, they both mean the same thing. All right, so let's start with the anode now. And basically what you can think about is you can use the cell diagram to figure out what's going on. In the anode compartment, reading from left to right, what happens? I start with zinc as a metal. What happens to it? I form zinc cation. Okay, that's all written down. The only other thing I have to add to this is I have to say, okay, that's a 2-electron oxidation. And again, that's something you can figure out from the half reaction. Okay, If I start with something with no charge and I go to something with a +2 charge, that means I've taken away 2 negative charges. Similarly, if I go to the cathode, or excuse me, to the anode, get to the cathode, excuse me, I start with copper 2. And I produce copper metal. So I'm going the other way. That's a reduction. All right, so those are the two half reactions. Now, I can write the net reaction for the cell by adding these two things together. It's another application of Hess's law, if truth be told. All right, what do I get? In this particular case, if I'm going to write a net ionic equation, the first thing I need to make sure is that my electrons are balanced, which they are, so I don't have to worry about that. So I just simply add these two things together. And it really doesn't matter what order the reactants come in. I'm just doing them the way they appear here. Same with the products. Okay. So, how can I use half reaction potentials to determine this? I can look them up, and if I know how to manipulate them, all I have to do is add them together. Okay, so I'm going to write two things over here on the left side, or excuse me, on the right here. I'm going to write E0 reduction. Okay, and I'll explain why I do that in a second. And then I'm going to write E0. Okay, so here is one example of a table of standard half reaction potentials. All right, this one comes from another textbook. Your textbook, I think, does this upside down, if I remember correctly. Some books do. I think Alex does too. All right, they start with this bottom half reaction instead of the top half reaction. Okay, and from some perspectives that makes more sense because you're starting with the highest value and you're working down. In this particular case, you're starting with the lowest value and working up. Okay, so let's look at these things. Let's start with this first half reaction here. This is the reduction of lithium cation to lithium metal. And according to this chart, that reduction half reaction has a potential of negative 3.04 volts. Now, what I want you to understand is that is not the half potential for this half reaction. That doesn't exist. This potential is referenced to this. Okay, so what do I mean by this? Basically, what I mean is this. If I make a cell, let's see if I can find a room to do this, where the half reaction that is shown here, okay, and the way you do this is you put a platinum electrode in here. You have H2 gas at 1 atmosphere. And you also have hydrogen ion in a solution at a concentration of 1 molar. That is your anode right there. Your cathode would be this, a 1 molar solution of lithium ion and then lithium metal. All right, so basically what this is saying is if you make this cell, then the E0 of this cell, as it's written, is negative 3.04 volts. Okay, so every half reaction potential on this table is referenced to the reduction potential, or the half reaction between hydrogen gas and hydrogen ion. That's what this is saying. And notice also how they list it as H plus here instead of H3O plus. That's one of the reasons why I show acids as H plus as well, because it corresponds with this, what you're seeing here. Okay, so what does that mean for us here? Well, we have to find two half reactions in this table. Let's start with the reduction, because that's easy. Here's the problem we face, though. There are several reduction half reactions involving copper, and specifically two that involve copper too. This first one is right here. Is that the one we want to use? Does that correspond with the half reaction we have written here? The answer is no, because the products aren't correct. In this case, the products are copper 1 ion. Okay? On the other hand, the second one, which happens to be conveniently right below it, is the one we're interested in. Okay, so according to this table, with respect to the standard hydrogen electrode, as it's called, SHE, this half reaction has a potential of positive 0.34 volts. Okay, let's write that down. The standard half potential for this half reaction is positive 0.34 volts. Okay, now the standard potential with respect to our net reaction is going to be the same because we have not changed anything about this half reaction. In other words, we have it written for our cell as a reduction half reaction. Whoops, sorry, I went the wrong way. Okay, now let's find the oxidation half reaction. We're not going to find that because none of the half reactions on this table are written as oxidations. They're all written as reductions. So we have to turn it around. All right, if we think about it in that perspective, here it is. There's only one half reaction involving zinc in this entire table, so it's not nearly as confusing as it is for copper and for some of the other transition metals. Okay, that's all we have to think about. But it's written as a reduction. We have it written as an oxidation. All right, so according to the table, the standard reduction potential for zinc with respect to hydrogen is negative 0.76 volts. But just like with state functions, because really this is tied to a state function, and there's no logarithmic relationship here. If I flip the half reaction around, I change the sign. So, if I want to figure out the E0 value for this cell, all I'm going to do is I'm going to add these two numbers together. The standard oxidation potential with respect to hydrogen for the anode reaction and the standard reduction potential with respect to hydrogen for the cathode reaction. And so what that tells me here is that I would predict the standard potential for this cell to be positive 1.10 volts. Okay, last thing I'm going to show you before we go, just to really briefly, is your textbook tells you to do it this way. They say just use the reduction potentials. And so if you were to do it that way, you would take the reduction potential for the cathode and you would subtract from it the reduction potential for the anode. It still gives us the same answer. Okay? It's a shorthand way of doing this. My hope is that by the time we finish this, which we will do next Monday, you will understand why I think it's important to write this out. Okay? Perhaps not so much so just for doing what we've done here. But if we're going to talk about non-standard potentials, which is something we'll get into next time, on a week from today, then you have to be able to do this. And you have, and there's a very good reason why. All right. We are finished for today. We will pick up with that again in a week. And you have your next exam coming up on Wednesday. And sorry about the technical issues earlier, but Zoom, I've had to reload Zoom on this computer about 5 times so far this semester, and every time I do it, it makes a mess of things. All right, see you all Wednesday.